In the name of Allah, the most gracious, the most merciful. Now, inshallah, Rabbil Alameen, we will talk about section 3, the optical phenomena. In this section, we will study 4 main phenomena. We will study the total internal reflection, atmospheric refraction, dispersion, and lens aberration. Okay, number 1, this is the first phenomenon that we will talk about, which is the total internal reflection. If we consider the following situation, now this is a boundary, okay? This boundary is between 2 media or 2 mediums. The first medium is here, it's denser. So here we have denser medium, and when I say denser medium, I mean more or higher refractive index. So this is the first medium, so it will be the NI. NI, you can say it's initial, but in fact it's incident, okay? So here, if the source of the light is here, the incident ray will be in the higher, in the denser or higher refractive index. And this light, for example, this is water, okay? And here we have air, which is lighter or less dense, less density, okay? And less refractive index. The light will be refracted in this medium, so it will have the symbol NR. The refractive index will be NR, it's less. Well, we have 3 main situations. The first situation, if the light falls perpendicular to the boundary, okay, what will happen? It will go straight, okay? We explained this point in the previous sections, okay? If the light falls like this, it will bend far from the normal, far from the normal. Why far from the normal? Because it goes from higher density to lower density. So here theta R will be theta I, as we explained. Here theta R equal 0, and theta I equal 0 also. Well, as we increase the angle of incidence, the angle of refraction will increase till we will reach a very, very important situation where this is the incident ray. The incident ray will refract as maximum as possible. It will give the maximum possible refraction. In this case, the angle of refraction will be called, or will be 90 degrees. The angle of refraction will be what? 90 degrees. In this case, this angle of incidence that made angle of refraction 90 equal or called critical angle. Why is it critical? Because the critical angle here gives special case, gives the maximum refraction, which is the refraction with an angle of 90, okay? So let's see here. The critical angle is the angle of incidence at which the refracted light makes an angle of 90 with the normal, okay? So it's identical to the what? It's identical to the surface or the boundary. Well, the question now, what will happen if the angle of incidence becomes more than critical angle? The answer is no refraction will happen. So what will happen, Mr.? Total internal reflection. The light will move in this direction, then it will reflect to the same medium and will not pass to the other medium. Okay, it means what, Mr.? It means this is not refraction, it's reflection. Someone may ask me, Mr., so why didn't we call it reflection? Why total internal reflection? Because in this case, in the normal reflection, some rays reflect and other rays are absorbed or refract inside the matter. Okay, but in this case, no rays absorb nor refract. All rays, 100%, will be reflected to the same medium. Well, so in the incident ray, if the incident ray is in the denser medium, remember these three conditions. This situation will happen in the following conditions. If the incident ray or the source is in the denser medium or the higher index, if it falls to the boundary with or to a less density medium or lower index with an angle, if the angle of incidence is more than the critical angle, what will happen? Total internal reflection will happen. Okay. Alhamdulillah. Sorry. So it doesn't refract to the less density medium as usual, but it reflects totally 100% reflection to the same medium, which is the higher one, which is the denser one. Okay, that is what we call the total internal reflection. Okay, this diagram or this figure shows a schematic diagram. This is the normal angle, and the refracted angle, the angle of incidence and the angle of refraction are zero. Okay, here as we increase the angle of incidence, the angle of refraction increases, and so on till the angle of refraction reaches a maximum value, which is 90. This case, the incident angle, the incident angle is called theta C, critical angle. Okay, and any angle of incidence more than this angle, total internal reflection will happen. So what is total internal reflection? It's the complete reflection that takes place within a substance when the angle of incidence of light striking the surface boundary is greater than the critical angle. Well, here, this figure shows us an experiment of beam of rays. Those show the different cases shown in this figure. Well, now, what are the applications of this phenomenon? In physics, we know that we don't study application just for fun, okay? But we study the phenomena Allah Azza wa Jal put in the world to use them in applications, okay? The applications of total internal reflection, okay? Number one, the appearance of diamond. We know that the diamond has some wonderful appearance. What is the source of this appearance that gives this importance or this good appearance of or good value or high value of the diamond? Okay, it's the total internal reflection. Why? Because the diamond has small critical angle. So its faces, when its faces are cut in some way such that the light enters, and when it reflects inside the diamond piece, it undergoes total internal reflection. It gives this appearance of the diamond because the light undergoes internal reflections inside the diamond. Okay, well, okay, so sometimes you feel as if the diamond makes something, sometimes different shapes like mirrors inside it. Okay. Number two, reflecting prism. This is the reflecting prism. Okay. This reflecting prism is made of some kind of glass whose critical angle is small, which is approximately 42 degrees. So this is designed such that when the light falls perpendicular to the first phase, it will go along its path. Then it will hit this side, okay, with an angle of what? 45. And the angle 45 here is more than the angle of critical angle, which is 42. So it will undergo total internal reflection to deviate with a normal angle. It will make normal angle like this. Okay. Number three, fiber optics. Fiber optics are tubes, elastic tubes like we see, okay, made of plastic or transparent materials. Okay, these tubes are designed such that its substance has small internal critical angle, so the light enters from one terminal and deviates several total internal reflections to come out of the other terminal. What's the importance of this? This is used in telecommunications and communications. For example, the internet. Okay, when we use the electric signals to transfer the data, okay, it was so slow. Why? Because it depends on the data were carried by the speed of the electrons, okay, because it was electric cables, okay. But now the cables are made of optical fibers like this, okay. Here the data are carried by these waves, okay, these light waves. So it travels with the speed of light, okay. So in communications, okay, and in medicine, like the endoscope, you know, the endoscope, they use some tube and enter it, for example, from the mouth of the patient, okay, till the internal parts of his digestive system and so on, okay. In the beginning or at the end of this tubes, there is a camera, okay. This camera can show the physician or the doctor what's inside the small intestines and so on, okay. Well, now we will learn how to calculate the internal the critical angle, okay. From the Snell's law, we know that Ni sine theta I equals Nr sine theta R. In the critical angle, theta I will be what? Will be theta C, which is critical angle. So we will say that Ni sine theta C equals, let's remember that, when theta I is theta C, when the angle of incidence equal critical angle, what will happen? Theta R, which is the angle of refraction, it will be 90. Okay, this is from the definition. Okay, so Ni sine, we will substitute here. Ni sine theta C equal Nr sine what? Sine 90. Okay, sine 90, it's 1. So Ni sine theta C equals Nr times 1, which is Nr. So to find theta C, sine theta C equals Nr divided by Ni. Okay, remember that. Nr is smaller than Ni. Okay, because sine, any sign should be smaller than 1. Okay, well, and to find it, we can use the shift in the calculator. Okay, we can use shift sine or sine -1. Okay, so this is the formula that we will use. Sine theta r equal nr, theta c equal nr divided by ni. I hope it's clear. Well, let's have an example. Find the critical angle of water-air boundary. Okay, here the question says water-air boundary. If the index of refraction of water is 1, so this is n of what? N of what? N of water equals 1.333. So Ni, this is Ni. Why? Because N of air equal 1, approximately 1, as we said, okay, in the previous lectures, okay? So here, which is smaller? Let's remember that. Sine theta equal, theta c equals what? The smaller, which is 1, divided by the larger, which is 1.333. Then find the answer. And so we can write that theta c equals shift sine, the answer, sine to the power of -1, 1 over 1, 3, 3, 3, okay? And the answer will be as the following, okay? So theta c equals sine theta 1 over 1, 3, 3. So the answer will be this. Well, now inshallah, we will talk about the optical phenomena, or the second optical phenomena, which is the atmospheric refraction. Okay, the atmospheric refraction is responsible for the image of the mirage. Okay, the mirage is a phenomenon that's produced by the bending of light rays in the atmosphere when there are large temperature differences between the ground and the air. So it happens in the too hot days, okay, and there is some kind of inverted mirage which is formed in the too cold regions. Okay, here total internal reflection happens. Total internal reflection happens. Well, so this is the image or the top of this tree. Okay, the ray that's coming from the top of the tree is undergoing some refractions, then total internal reflection, then it reaches your eye, okay? And this is another ray that's coming parallel to the ground. It doesn't undergo any bending because it transfers in the same temperature or in the same layers, okay? Now, your eye is, or your eye can see the object or the image along the ray that's coming to it. Okay, so here you see your eye will see the image where at the end of this ray, so it will see the image of the top of the tree at or on the ground. Okay, and your eye is used to see this case in on the surface of water. So you see as if there is water on the road, asphalt or deserts or something like that. The third optical phenomena is the dispersion. And we talked about dispersion in several details in the last term, but we will explain it again. Dispersion is the process of separating polychromatic light, like the sunlight, into its components or component wavelengths as happening as it's happening in the present. What is the reason of this dispersion? The reason of this dispersion is that each light has its wavelength, so, or has different wavelength, so each color, okay, color, okay, so it has different refractive index, so different angle of reflection. So they enter the glass together, but when they enter the glass, each one deviates or refracts with different angle, so they are separated. We explained this several times in the last quarter, as I remember. Well, here, the rainbow is an application of this phenomenon. The rainbow here happens because the droplets of water in the atmosphere act as tiny prisms, okay, where two processes happen. The sunlight is coming from here like this. It enters the droplet, then separation happen. So number one, dispersion happen. Number one, dispersion happens. Dispersion happens. This is number one. So this is the first step. Dispersion. Okay, like this. Dispersion. Okay. Then here, what will happen? Total internal reflection. Total internal reflection. Okay. So number one, dispersion. Number one, dispersion. Number two, total internal reflection, then they come out of the drop or droplet of water to give the rainbow. Well, the last phenomena that we will talk about is the lens aberration. The lens aberration is some way looks like with difference the mirror, the spherical mirror aberration. Okay, but here the aberration is called chromatic aberration. It's focusing focusing of different colors of light at different distances behind the lens. Why? Because of the dispersion. The dispersion makes the white, sorry, the blue colors, the blue rays are focused in certain focus for the blue. Okay, the red rays are focused in or on a certain point, which is for red. Okay, so each ray has its own focus, and these foci interfere together to give the image with some interfering colors. Okay, this interference, not interfering, I mean overlapping colors or not clear colors. Okay, so this is called the chromatic aberration. And when I said interference, I didn't mean interference with the meaning of the interference of light. Okay, no, I mean two colors superpose and so on. Finally, the chromatic aberration can be greatly reduced by using of a combination of converging and diverging lenses made from two different types of glass. And Alhamdulillah Rabbil Alameen, we finished this section and our portion, and have a nice time. Assalamu alaikum wa rahmatullahi wa barakatuh.